Okay, folks, so picking up where we left off at the end of the previous video, um, again, for Math 51 students in my summer class this summer 2021, or for anyone who found their way to this video and wants to learn a little bit about the dot product. So we're going to pick up where we left off. If you're looking at this plane over here, this was from a homework question which I actually asked you for. And the part of it from the homework that I asked you to do was to find the magnitude or the length of these two vectors. So here, the blue vector v is the vector 3, 6. I'm using the angle bracket notation for vectors. We calculated in the previous video its length to be 3 root 5, or its magnitude. And we did the same for u. So u is this vector down here, 4, -2, and we found its length to be 2 root 5, okay? We're going to use that because we're going to introduce the dot product. The dot product is sort of defined or given in two different versions. And so the goal of what we want to do here is show that those two versions are equivalent. And then once we've done that, then we've sort of defined how to calculate the dot product. Then we will look at a couple of examples. So I've got an example I could run on my notes right here. And then we've also got, I kind of want to wrap up. This was question 6 from the homework already. So first of all, what is a dot product? Well, let's actually think about what we've covered in the previous video. So here I'm given two vectors, u and v. Okay, so I'm going to write given u and v. We can form, or we can create new vectors, which we did a few different ways in the previous video. So we can make scalar multiples, let's say. So in other words, k times u. So k is scalar times the vector, and then that becomes, overall, this that I'm underlining is a new vector, right? And I'm not sure if I wrote this in the previous video, but if u is u1 comma u2, right? If I've got two coordinate vector, then k times u would be k u1 times k u2. Okay, so we sort of multiply that constant, that scalar multiple, sort of distribute that in a way, you could say, or multiply it through all the coordinates, right? And so that was a scalar multiple. We said, so that would be, if I took multiples of v, it would be in the same direction. And then we said if k is larger than 1, it would be longer than v, right? If k was between 0 and 1, it would be some kind of length like that. If k was a negative value, we'd have sort of the reflection, or the opposite, negative v, and then we could scale that back or scale that longer. So that's the idea of a scalar multiple, but keep in mind, if we start with a vector u, then by making a scalar multiple, what we've got is a new vector, right? So a new vector k times u. And we did the same thing, and you could have kv, right? You can make scalar multiples of that. We also created sum and difference vectors. So we said u plus v, right? And we did that by adding, we said that would be u1 plus v1, right? So in other words, add your two sort of x coordinates or first coordinates, u2 plus v2, add your second coordinates, and that becomes a new vector. All right, so I'm using the triangle brackets there again. That became a new vector. We defined u minus v, which we said we had a little shortcut. Go to the tip of v. From there, go to the tip of u, and that shortcut to get you from tip to tip is the new vector. But this is the computation or the formula for it, right? We just subtract the coordinates. And again, that's given v would be v1, v2. Okay, so this was all covered in the previous video. So if you missed it, maybe double back, watch those. But the key idea here is, so what we've done here is given two vectors, or given a vector, we've created new vectors by either taking a scalar multiple of one of those vectors or combining those vectors through either addition or subtraction. So I could kind of do the plus minus and then carry out whatever operation you have. Okay. So the point of what I'm trying to say here is when we take two vectors and combine them using addition, we get the result is a new vector. When we take two vectors and subtract them, the result is a new vector, right? It was one of those other diagonals. When we take what we call the dot product, which is sort of like a version of what if I have two vectors and I want to multiply them, right? What would that even really mean? And so because we're dealing with more than one dimension here, we can kind of conceptualize that idea of multiplication in more than one way. So one way is what's known as the dot product, all right? In the next video that we cover, we will do what's called the cross product, which is sort of a different, what you could say, version. But for the dot product, what's important to note is the result is not a vector. it's a scalar, a real number. It's just a number. So in other words, u, if I've got a vector u dot v, and that's exactly how we read that. I don't say really u times v, because again, what does times mean? Multiplied. So there's going to be sort of two different versions of that. So we say u dot v, but the answer to what that is not a vector. So let's just say it's a scalar or a I won't say equals, I'm not writing a formula, but is not a vector, just a real number, meaning a scalar. All right. So what we'll see is the dot product is kind of a measure. It sort of measures something. It sort of measures the relationship between the two vectors, sort of like, to what extent are they sort of moving in the same direction as one another? That's how you could sort of envision that. So we'll look once we get the formulas up, and then we'll look at this. This is actually a kind of an interesting example from the homework. Then we'll work another example as well. All right. So anyway, though, that's I just wanted to cover that. It's going to give us a number, not a new vector. So it's somewhat different than the previous things we've looked at. So what you see on your page, if you're in my Math 51 class, you've got the notes. We're on page 3 of some linear algebra. And so you're given a couple things. They give us the definition. So let me just write it here. Definition. And so a lot of things, some things in this class, I give you a couple definitions and then we use those to prove other results, right? We did that a lot with those number theory things. And so some of those results are like proven results, theorems, let's say. But a definition, you don't need to worry about like, why is that true? Or how do we know this is true? It's just, it is true because that's what we're defining the dot product to mean. So we're kind of telling you what the symbol means. And so our definition of u dot v, on your paper, it's just the bold u dot bold v. But remember, the boldness is a way of indicating vectors. So on the board, I just use those little vector symbols. Is defined as this. So it's the magnitude of u, so the length of whatever my u is, multiplied by the length of v, multiplied by cosine. So let me do this, because I'm noting, again, if you're in my class, you're reading the notes. U dot v, if you can tell on your printed page, that dot is like a big bold dot. Then we did use multiplication here. U is just a number, so you kind of have to think about, what am I multiplying? The absolute value of something, right? Those absolute values of the vector u, that's really a number, that's a scalar. So then I am going to do multiplication. So I've got the absolute value of u times the absolute value, or the length of vector v, times cosine of the angle between the two vectors. Okay? So what does that mean? That means if I've got u and I've got v in any orientation, then this angle right here, that is theta. Okay? So on the example that we'll do, sometimes we want to figure out what the angle is. So we'll use a calculator, we'll use the inverse cosine operation, we'll figure out what some of this stuff is. Alrighty. But so that's what we've got. That is a definition of what the dot product is. However, that one's kind of hard to work with computationally because, you know, how am I measuring this angle? How do I know the angle between the two vectors? And then how do I know what cosine of that is? So unless you do a lot of trig, or again, if you've got a calculator. But that's what our definition is. So some of the results that we're going to prove, we want to know a little bit about cosine. So depending on how familiar you are with trigonometry, if you've ever really studied it or not, you know, we'll leave this for what it is now. I'll start talking about some specifics to do with cosine when we get to some specific examples as needed. But that's the definition of the dot product, okay? So again, this is u is a vector, v is a vector. So I've got vector u, vector v. I've got an angle between them. What we're doing here, what this dot product is, it's the length of this vector multiplied by the length of that vector multiplied by whatever the cosine of that angle is. So in other words, scalar, scalar, scalar. So these things are just scalars, and the result then is a scalar. Meaning, again, just a number. So it's like a value, but it doesn't have like a direction or anything associated with that. Okay. Cool. So that's our definition. We will use that again if we want to answer questions like, what is the angle between those two vectors? But that's not really the computational friendly definition. So there's sort of an alternate, I don't know if we want to say alternate definition or alternate representation. Let me just put like a star here. In other words, this is how we calculate these. U dot V, and we can extend this idea to higher dimensions. So if I've got x, y, z, right? If I've got 3 coordinates, if I've got more than that, but I'm basically going the idea of being on this flat plane. All right. So u dot v is, and I can label up what u1 and v1 are, but it's u1. Let's think of this actually earlier. U plus v, right? U being u1, u2, right? V being v1, v2. How did we do plus? We added the first 2 coordinates, right? We said u1 plus v1, right? And then how did we get the second coordinate? We said let's just add them, u2 plus v2. All right, that's similar to what we're doing here. So assume u is u1, v1. I'm sorry, u1, u2, v1, v2. So I'm going to take the product of the first 2. So u1 times v1. Notice I'm using the small dot to indicate multiplication. And you could just write those 2 next to each other without a dot also, as we do sometimes for multiplication. But then what I'm going to do is I'm going to add that. Notice I'm not, so this, right? U plus v is a vector, a new vector. So it has a new sort of x-coordinate, new y-coordinate with a comma in there, right? So we're using that vector notation. U dot v we said is a scalar. It's just a number. It's not a vector. So there's no parentheses. What I'm going to do is take u1 times v1. I'm going to take u2 times v2. And then I'm going to add those 2 together. Okay? So the result of doing that is just, again, it's a number. It's a scalar. It's not in brackets. It doesn't have a direction or anything like that, right? We're literally taking the 2 sort of x-coordinates, multiplying them together, the 2 y-coordinates, multiplying them together, and then adding that result. Okay, so computationally, this is the formula. You know, if you're given 2 vectors like this, u and v, this is the formula you will use right there. All right. So what you were asked to do on the homework is, find, we were given u and v. So in part A, it says find u, find v, and then find the cosine between the 2 angles. And so we had, in class today, we hadn't covered this definition, so you wouldn't really be able to do that. How are we going to do that here? What we're going to do is, I know that, let me put it this way, and then, because before we embark on that homework problem together, what I really want to show, or want to prove, and we're going to prove this together, is that notice that this, u1, v1, right, plus u2, v2. In other words, if I actually do this, if I do the sort of computational version of the dot product, I want to show that actually does equal this. That if I take the magnitude of one vector, multiply it by the magnitude of the other vector, and multiply that by the cosine between those, right? So in other words, is this really true? Right? Because I just told you that I told you u dot v equals this. And then I also, and again, that one's a definition, so I don't have to worry too much about proving that, because the definition's like, you know, let there be light, and then this is true, right? So that we're defining that to be true. But this is sort of a computational result. So before we jump into the homework problem, I want to go together prove that this is true. And I've got a little proof. That's what the blank space in the notes is for. Sort of right here in your notes, it says we will prove that the 2 definitions are equivalent. So we're going to do that together. Then once we do that, then we can jump in together and finish up the homework problem. Alrighty. So I want to do that. Let me collect my thoughts for 1 second. And then we will go forward. So, yeah. Anyway, so once we're done, how are we going to answer the homework question is if I can use, once we prove that both of these are legitimate, then given u1, u2, and v1, v2, I can figure out numerically what is u dot v, right? Based on these 2 vectors. What is u dot v? What's the number? Then now we also know the lengths, those 2 lengths, and so we can sort of solve for cosine of the angle and then figure out what that angle must be. So we'll work that together. But I want to show that this equivalency, I want to show that both of these versions work. So let me erase this. I'm still leaving this graph up just because I want to, because at the end we're gonna discuss, find the angle between those things, and I want to see if it looks accurate. Those two vectors are chosen sort of particularly. All right. So what we're going to do, and what your notes say right there, it says we will prove that the two definitions are equivalent, those two expressions that we had right there. But in order to do that, we're going to recall the law of cosines. So you may or may not be familiar with the law of cosines. If you are printed, let me draw on the board here what I think you see on your paper, if you're my 51 student. And then I'm going to edit it because there's something wrong with that. I see 3 dots because my copy has printed dots and then has pencil drawn in. I see 3 dots and then I see A, C, B. That's actually wrong. So if you've got this on, if you're following along with your paper, we want to switch the C and the B right there. And the reason is, I'll show you why, is I want to consider a triangle here. Right? And here's my angle theta. Okay, so what the law of cosines says, because you may not be super familiar with the law of cosines, the law of cosines is kind of like a general version of the Pythagorean theorem. Pythagorean theorem says this: if I've got a right triangle, right, and let's say A, B, and then if I've got a right triangle, the side opposite the right angle we call the hypotenuse. And typically for the Pythagorean theorem, we would say do something like that. And then c squared equals a squared plus b squared. That's for right triangles. So actually, let me label that over here. For right triangles. And a lot of folks know the Pythagorean theorem and, you know, can rattle it off really quick, and then they know it's associated with triangles. And sometimes it's sort of an afterthought, or it gets you know, we might not realize, but that really only holds for right angles. This law of cosines that I'm about to draw, let me erase this and write law of cosines, which we're going to use to prove that those two statements earlier were equivalent. The law of cosines is more general, but the idea is it's going to involve cosine of an angle, and I want the side opposite the angle is still needs to be called C if we want everything to line up. Okay, so on your, again, it was only half of it was printed there, the letters and the dots, but it should read like that. Okay, and so what the law of cosine states is this: C squared. So I'm gonna write out the law of cosines, and then I'll mention how it actually is the Pythagorean theorem because of the particular angle, because that's a 90-degree angle right there. It's a squared plus b squared minus 2ab times cosine of whatever angle I'm dealing with. Okay? Now, what's important though here is that so I could write this more details out so it would be super specific, but I'm just stating them verbally. Theta, this is a Greek letter theta, this little sort of circle with a little line. That's a Greek letter theta. It represents the angle. C has the side that is isolated over here. Theta is the angle opposite that, or C is the side opposite the angle. Okay. In other words, I could write this differently. If I called this angle, let's say alpha, I could do it now, but now that would say b squared, right? Because b is opposite alpha. So then it would be b squared is a squared plus c squared minus 2 ac times cosine of that angle, right? So we're only dealing with one angle here, but in other words, if you're wondering how this formula sort of works, that's the idea, is you're solving for sort of the square of a side opposite that angle. Okay, these other two sides then are sort of interchangeable. It wouldn't really matter. But that's important, and so the letters on the page printed on your page, the B and C were opposite, and so it doesn't really hold up. So yeah, and then if I called this, you know, beta or whatever, gamma, I could label the other letters different, the other angles, and set those up. But that's true, okay? So let's imagine now stretching that theta up to like this, and then we have this angle. So theta is a right angle. Well, that would mean that then for the particular case here, I would have minus 2 length A times length B times cosine of a 90-degree angle. All right, and if you do remember trig, cosine of 90 is 0. Okay, so then that means this whole thing becomes 0. And so you've just got a squared plus b squared, just the square of the two things. All right. What happens is we have these other angles, and theta could be larger than 90 degrees too. So you could have something like that could be your theta as well. But then this formula holds up as long as C is your opposite side. And we wouldn't really call it the hypotenuse. It's just sort of arbitrary, but with whatever angle we're dealing with. Okay. So anyway, if you're not familiar with this proof, with this rule, or law, I'm not going to prove it right now, but it's true. And I want to use that, though, to prove the dot product equivalencies. So we've got that picture. We've got this sort of law of cosines right there. Now let's think about, I want to set things up. So this is going to be kind of let's put a dot here. Consider that sort of the origin. If I've got a vector u right there, and I've got a vector v right there. Okay, so what I'm trying to do is kind of draw a triangle, but now with some vectors going on. If I've got u and v, then the third side of this triangle, and it depends where I want to go, but let's say I go from the tip of u. Remember, u minus v was from the tip of v to u. Okay? I don't know if this is helpful. I was thinking of this between videos, but if you guys are Beatles fans, there's a Beatles song, From Me to You. Right? So from V to U. So I'm going to go from V to U, and that's U minus V. Maybe that's not helpful at all, but good song. Okay, so now I've got that little triangle right there, all right? And I've got some kind of angle theta, the angle between U and V. So that was one of the, earlier we said the dot product, U dot V, the real definition was length of U times length of V times the cosine of the angle theta between the two vectors, right? So that's what we've got right there. So we're sort of trying to set that up. And so what I want to show here is that u dot v is also equal to u1 v1 plus u2 v2. Meaning component-wise, coordinate-wise, if I multiply those two first coordinates, multiply those two last coordinates, add them together, then numerically I'm going to get the same thing as that, right? So that's what we're trying to show is that equivalency. Okay, so I'm just going to kind of jump in with some notes here. What I want to do is start with u minus v, and I want to do this. What I want to do really is write that for the law of cosines, right? So here's my law of cosines, and that relates to this triangle. Let me get rid of that alpha. That was that little goldfish looking guy. I had ABC. Theta is the angle across from C. And then we said C squared. So the length of that side squared is equal to the sum of these two sides squared sides minus 2AB times cosine of that angle. So let's see what we've got over here. So that means C is U minus V. Right? So I've got U minus V, absolute value or length of that squared. Okay? Because C, when we think of ABC here, we're thinking of the length of those lines. So I've got the length of that sort of diagonal line right there, squared, is equal to what's in place of A. So I'm just filling in, right, just substituting for one picture. So A squared is the length of U, so magnitude U squared, plus B is this base right here, so magnitude V squared, all right, minus 2 times UV. Let's see how I want to write that out. U, V times cosine theta. Kind of squeeze it in right there. Alrighty. Why am I putting absolute value bars on everything? Let's think about that. Because remember, the absolute value, A is a length here, right? We think of when we do the Pythagorean theorem, we're thinking of a length right there, which is just a number. There's just a number associated with that. So we want sort of the scalars, the absolute length, absolute value of the length of those vectors right there. So that's what I've got. So all I really did right here is fill in anywhere where I saw A, I put the absolute value or the length of my vector U right there, because that's side length A. Anywhere I saw B was vector V, and C is U minus V, right? From the tip of V up to the tip of U. Okay, so let's see what we've got. What I want to do now is I'm going to start using some of the formulas. So I'm going to try to write this up. Remember what we said for the magnitude. So magnitude of U, we actually found that, oh, I'm sorry. That's for the example problem, those red and blue. So this is just in general. But let's think about how we did all this. I'm going to do this and then I'm going to write them up here. absolute value, or the magnitude of u was u1 squared plus u2 squared, right? And then square root of that. That was from previous video. And so then since u minus v, right, its first coordinate is u1 minus v1. So I'm going to have u1 minus v1 squared, right? And then plus u2 minus v2 squared in a radical. Alrighty, so that's that thing. What we have here is absolute magnitude, so we can square that since I've got over here and get rid of the radical. All right, so that's the idea. That's kind of what I'm filling in now. So it's going to get a little bit busy. Let me put these over here. I've got my u, I've got my v, I've got my u minus v. Upwards like that, I've got my theta, and let me lose that. Okay, and again, if I square these things, I can get rid of these radicals here. So again, this was just our distance formula or our magnitude formula from page 1 of these notes. This is that because u minus v, if we say what that is, u minus v is u1 minus v1 comma u2 minus v2, right? So now I've got x coordinate squared, y coordinate squared, add them up. There we go. So that's what we are looking at. So what is that going to become? This right-hand side then is this. So I've got u1 minus v1 squared, which let me see if I can distribute all that out as I go. Because I'm going to write all this. That's going to give me u1 squared minus 2 u1 v1 plus v1 squared. All right, agree? So I'm going to just do this to try to save some time. This thing, I'm squaring it, right? So I'm getting that. Okay, so then I've got that. Then to that, I'm adding this one, u2 minus v2 squared. So that's going to be plus, I'm going to get u2 squared, right, foiling these things, minus 2 u2 v2, minus 2 u2 v2 plus v2 squared. All right, so in other words, that guy foils out to those three terms, plus this thing foils out to those three terms. All right, and so that's my whole left-hand side. That's u minus v magnitude squared. There we go, and then foil it out. Okay, so just trying to save a little bit of space right there. Let me get rid of that. And keep working here, keep my eye on that clock. So all of this right here is left-hand side right there, is equal to now, and remember, this is just the law of cosines, which we're taking for granted, so everything I'm writing here is factual. Absolute value of or magnitude of u squared. Remember, magnitude of u was u1 squared plus u2 squared. Magnitude of u is that thing wrapped in a radical, but then we're squaring it, right? So I can drop the radical. Plus v1 squared plus v2 squared. Again, magnitude v is that in the radical, but then I've got squared that, right? I'm squaring those things so we can drop the radical. So that's nice. So here I've got magnitude u squared plus magnitude v squared minus 2 magnitude u. So now I've got radicals popping in here. Magnitude u is square root u1 squared plus u2 squared, right? Because those guys aren't being squared, times root. Actually, let me just keep those in magnitude form. Times cosine theta. Okay. In other words, why do that? Because look what we're trying to prove. The dot product is magnitude u times magnitude v times cosine theta. What were we given? Once we said A is really magnitude u, B is really magnitude v, then what do we get? Then right here we've got that, right? That little tail end is what we're trying to get to. So we're in pretty good shape. Let's see what we're looking at here, because I'm going to do some cancellation, some circles to sort of cancel things out. Because what we've got here, we had this, right? U minus v squared is equal to this entire red expression. So then the green expression, that's all this. That's this whole line is equal to the red expression is this whole line. right there, right? So I've got that is equal to that. So let me try to cancel some terms out. Just be sloppy about it here. In other words, what do we see over here? U1 squared and a U1 squared, right? So I could subtract those sort of from both sides or cancel those from both sides of the equality. V1 squared and V1 squared, right? So I'm kind of subtracting this. My left-hand side, my right-hand side have it both. U2 squared, get rid of that. V2 squared, cancel those out. We're just subtracting from both sides. Alrighty. So what am I looking at now? What I've got left over here, I've got a -2 and a -2, so let me factor that out. -2, U1, V1, right, plus U2, V2. Looking familiar, right? That's this. That's the computational dot product right there. And then we factored out that net -2. What do we have over here? -2 times absolute value or magnitude U, magnitude V, times cosine of the angle between those two. And so what can I do now? Divide both sides through by that -2. Right? Cancel that -2 out. Cancel that -2 from both sides. Or multiply both sides by -1/2. However you want to manage that. And there we go. Right? These parentheses, that was because I had factored out the -2, so I could distribute. But let me get rid of those. There's no point here. This is not a point or vector. It's a scalar, right? U1, V1. It's the product of those two coordinates right there. Okay. So for whatever that's worth, that's a proof that these two representations of the dot product are actually equivalent, because right here we're showing that this one representation, the computational, is really equal to sort of the definition, and that comes from law of cosines. Okay, so if you're like the backtrack type, or you like origin stories, right, or you want to go back, you could investigate a law of cosines proof, but that's for sort of another class, another time. Alrighty. Okay, now we've established what the dot product is. And so let me wrap up the homework problem. And then this thing is getting a little bit long. I may do another video maybe to wrap all this up. But let me finish that homework question. So let me jump forward a little bit. What is U dot V? Now that we understand what a dot product is. So according to our formula, it's U1 times V1 plus, and then U2 times V2. Okay? And I don't need any kind of brackets really, and it's not a vector, it's not a point, so I won't really do that. So here we go, is U1, U2, or my U coordinates, V1, V2. So I've got 4 times 3, and then plus over here I've got U2 is -2, times V2 is 6. All right, so in this case, I'm getting 12 minus 12, or plus -12, equals 0. So the dot product is 0 there. That actually means something interesting. We had these earlier, but now we know 0 is equal to. So I've got 2 root 5 is that length, times 3 root 5 is the length of V. Okay, times cosine of the angle. So if this was not 0, what I could do right now is to find the angle is I could sort of divide both sides by these, move these things over here by division, and then have cosine of the angle is whatever this value is, divide the dot product divided by those two things right there, and then I could do a inverse cosine computation on my calculator. I could do that. The thing to note here, though, is if I've got a product, 2 root 5 and 3 root 5, I could actually figure 2 times 3 is 6, and then root 5 times root 5 is 5. So this is 30. 30 cosine. The thing is 30, that's a non-zero number. So if this equals 0, that means cosine this must equal 0 right there. And so then the question is, cosine of an angle is 0. What's that angle? And that angle is a right angle, 90 degrees. All right. Not going to prove or establish that yet. That's based on some trig exercises, which we could do. But that's true. I mentioned that earlier when I said that the Pythagorean theorem is really a specific case of the law of cosines, right? When the angle is 90 degrees, because cosine of 90 is 0. But if we take that for granted, then we can say, hey, look, that's a right angle. And so I set this up. The reason why I've had this present on the board throughout the 2 videos so far is because I set it up in advance. I wanted to measure these things, mark them. There was 2-inch increments right there because I wanted the X and Y scale to be the same, so we can kind of see that that does look like a nice right triangle right there. Alrighty. There we go. Let me just say that, actually, I'll leave that for another video. So let me get rid of this. Let me press stop. This video and the previous one are both around 35 minutes. So, so yeah, I will follow up with a couple of examples for some dot product, perhaps, and then move on to the cross product. Alrighty.